So I'm coding and building this LLM from scratch that I will be training. And in today's video, we will learn everything about optimizations, how to make the LLM train faster from scratch, how to make it use less memory, how to train it with more quality. So you will learn how to improve efficiency, speed, and quality of your custom LLM from scratch. So we will learn about int8, FP8, custom fusion kernels. Here I'm gonna be scrolling, I'm gonna present all of this. There are so many things that we are going to learn in this video about optimizing a custom LLM. Here we have torch.compile and we have mode reduce overhead and mode max auto tune. What are the differences? So torch.compile is a part of Torch Dynamo introduced in PyTorch 2.0 to optimize models by compiling them into faster code under the hood. Normally, PyTorch executes operations one by one using the Python interpreter. Torch.compile captures your model and rewrites it into optimized backend code like C++ using technologies like Torch Dynamo and these ones, and Torch Inductor. I have a video about this, my last video. I will leave some links below so you can self-study this or you can self-study this. So what does dynamic false mean? Dynamic false tells PyTorch assume fixed input shapes. This enables more aggressive and static optimizations. Example, hard coding tensor sizes in the compiled code. It's great for stable batch sizes or models that don't change input shape frequently. If you set dynamic equals true, the compiler has to prepare for any input shape, which is safer but less optimized. So if it's not dynamic, it can hard code tensor sizes. It can just check the size and hard code optimizations. What is mode in torch.compile? The mode controls how aggressive and what kind of optimization strategies are applied. Reduce overhead original focuses on lowering compile time, cost, and quick execution. Good for smaller models or quick experiments where you want faster startup and minimal compile time. It sacrifices some runtime performance to avoid overhead from compilation. So in my code where I'm coding my LLM, I want to, let's say, test some new feature or check if there are bugs. I don't want to compile all of the things so long every time I try to test it. I just want a quick compilation. I want to check if my code works, if the compilation works, if my code works. So that's why I will use reduce overhead. Overhead just means like before testing the code, I have to compile all of this and all this extra stuff. So think of it as optimize a bit, but don't spend too much time compiling. And then we have max autotune, which is the new changed code that I set, focuses on maximum runtime performance, especially on GPUs. Uses auto-tuning, which tests different kernel implementations to find the fastest one. More compile time cost upfront, but can result in significant speedups during training or inference. So more compile time, but significant speedups. So this is when I've tested everything, I've decided to now run the training. So I will just now compile everything, spend a lot of time, so my training is fast. Think of it as take your time to compile and find the best performance possible. So we will use max autotune when we are training the large model, when we are deploying it for inference, when we are benchmarking for maximum performance. We will not use max autotune, but instead reduce overhead when we are rapidly experimenting with and need minimal startup delay, and we are working with a small model where compile time dominates. Next thing I want to do, if you see this Sage Attention paper, it's by Tsinghua University, released recently. So I just copied the whole paper and copied my code into Gemini and asked it to recommend any optimizations to my code based on the paper. So here we can check. Sage Attention argues int8 can be faster and more accurate for queries and keys in attention than FP8 on certain hardware like RTX 4090, so integer stored in 8 bits as opposed to floating point number stored in 8 bits. So we are currently using float 32 or float 16 for our calculations, but int 8 is significantly faster on many GPUs, probably on all GPUs that can support int 8. So those would be the later NVIDIA GPUs, for example. And for query key transposed, which is followed by softmax, precision loss is often tolerable if scaling is handled well. Yeah, so precision loss, we don't need such precision, 32-bit precision or 16-bit precision. We can just use 8 bits. Yeah, we are using FP16 or BF16, but this paper argues we should use int 8. So this is where we do it in our code. So there is this torch einsam, and then we are multiplying these q nope and effective key value for einsam. So this is just query times key. And then what to do? Quantize q nope and q positional embedding. So this has positional embeddings, this doesn't. To int 8. So add a quantization function. Quantize int 8 per token. Let's take a look at this function. Quantize int 8 per token. Goal is to quantize a tensor x from float 32 or float 16 into int 8 per token using per token scaling. This allows you to store the tensor in 8-bit integers while keeping relative precision. Step 1. Compute max absolute value per token. So x is the tensor, and we will take absolute value of the tensor. So all of the minus elements with negative will become positive, and then we will take absolute value, we will take the maximum in the last dimension, and last dimension is going to be the vector embedding. So list of numbers that represent the token embedding. So we will look at the token embedding and take the maximum absolute value number. And we will add a very small number because I believe we are dividing with this, and if maximum is 0, we don't want to be dividing with 0, so we will just add this very small number. It's actually, all of it is explained here, I didn't even see. So if one token vector is 0, 0, and then the whole vector, it's gonna be this tensor. So this is just showing the position, setting this position to this tensor. Then the maximum value here will be 0.5 because that's the absolute maximum, max absolute value. Then we will compute the scale factor. So we will divide maximum value by 127. So we map the largest magnitude value of plus minus 127, the range limit of int 8. The scale tells you how much 1 unit of int 8 represents in float space. So if you don't understand it, let's just continue. You will understand it. So scale is our max value divided by 127. So this is our scale. This means 1 unit in int 8 corresponds to around this many this value in float. The entire token will be scaled so the values fall within this range. And I believe whatever the maximum value is, it will be mapped to either one of these numbers, and then every other number will be scaled accordingly. So you can also use these materials. I will leave it below so you can self-study and ask questions if you don't understand. So now x int 8. So we will now transform x to int 8 values. So x divided by scale. So if you see here, if we have, for example, x to be 0.5, and this is the scale, if we divide 0.5 by the scale, we will get this number. As I said, we will stretch or squish values So they are between, so the one of them is 127, so they are in the maximum range. Okay, where was I? Here. So we will round and clamp. I believe that this should immediately be just around these numbers, but just to make sure, I'm not sure, maybe the computation doesn't have 100% precision, so just round and clamp. And then we will convert the data type to int8. Okay, so it's explained here, but I already explained it. So you see here, we have if x is 0.25, and this is the scale, we get 64 when we round this. So x 0.25 is going to be 64 in int 8. That's because our max value was 0.5. So it kind of makes sense that if 0.5 is mapped to 127, then 0.25 is going to be mapped to around half of 127, which is around 64, depending on the like scale factor, how much precision we did, and then rounding and then clamping. So we have a lot of these approximations. It will not get mapped precisely, but like this. And that's then we will return quantized tensor and the scale. So that's how you do quantization. You need the scale later to dequantized, i.e. reconstruct the original float value from int8. So x reconstructed is int8 times scale. So after we define this function, we have this step 2, k-smoothing before quantization. So before we use this function, we just defined it, remember. So goal, reduce outliers in k to improve int8 quantization accuracy. Now what is k, we'll see. Where in your code? Yeah, we have the key, outliers in key. Yeah, so in my key vector, we need to reduce outliers. What to do? Add smoothing before quantization. So I guess I would add these lines. So kv is equal to kv minus kv dot mean. Dimension would be second dimension. So that's gonna be sequence length. Now this is interesting because I don't know if this would mess up backpropagation, because we are modifying kv in place, right? I think so. We are modifying kv in place, so the backpropagation wouldn't know which version of this variable to use. So I guess we would maybe assign a new variable here and then use that new variable without changing this kv variable. That's how I think it would be. Step 3, FP16 accumulation for P times value. I guess probabilities time value, yeah. So the softmax scores, yeah, that's the probabilities. Matrix multiply value. Step using FP16 accumulators for speed. Why it matters? So float 16 is 2x faster on RTX 4090 than FP32, what I'm using right now. I also think this would not degrade performance significantly, and the performance degradation can be ignored or tolerated, maybe, but I don't know. We need to maybe test this. And I'm wondering, how would I even test this? This is such a small change. So I guess we just run the model, train the model, and I don't know. How would you test it? It's such a small change, and it's so hard to test model LLM for such small improvements or degradations. You won't notice maybe really if it writes a little bit worse. So PyTorch will by default use TF32 unless precision is set. So I guess we need to set to float 16 to use 16-bit precision instead of 32-bit precision. Step 4, fuse 1 over square root of d into dequantization scale. Goal, avoid a separate multiply with 1 over square root of d, fold it into int8 scaling. So this is in my code, so modifying scores with this softmax scale. what to do during dequantization of this matrix multiplication. See, we have scale q times scale k times the scale softmax scale. So this is going to fuse the operation, so there is no movement. We don't need to move data back and forth. We can do it all at once. And scores, score init32.float times final scale. Step 5, fuse quantization into apply rotary embeddings. We can fuse a lot of operations, it seems. Avoid extra memory operations by combining rotation plus quantization in one step. That's interesting. What's worrying me is that we would combine so many things in one step that our model wouldn't be so general anymore. But if I want to train as good of a model as possible, maybe I can like fork this model and then write all of these custom kernels for specific hardware and make it as specific as optimized as possible and then train it. This is where we have it in our code. So we have this Q positional embeddings part of the Q head, and we pass in the frequencies. So if I copy this, let me actually search for it. Ah, yeah, we have it right there. Yeah. So what to do? Update, apply rotary embeddings in the following way. If quantize, then we will quantize whatever this tensor was into int8, so either query or key, and we will return it. Then we just pass in this quantization, quantize equals true when we call this, and we will get the q vector and the scale to scale this back into original FP16. Then step 6, profile and adapt kernels per layer, optional. Goal, use different attention kernels per layer based on speed accuracy trade-off. What to do? Add a config per MLA layer, like use int8 query key true, use FP16 PV true, etc. Use profiling to determine best kernel variant. Example, use int8 for query key only versus full int8 training. Automate selection if accuracy drops are tolerable. This is complex but useful for large models. Summary and action plan, intake 1 for query key and matmul, speed up and difficulty hard, k smoothing before quantization, accuracy difficulty easy, FP16 accumulation speed up difficulty medium, fuse this, it's cleaner. I think there should be speed up as well. Easy, quantization fusion into rope, efficient. I don't know what do you mean efficient? It's all speed up. Medium, kernel selection per layer. Yeah, speed up, and this is harder. So these are all of the recommendations for speed up for our LLM. But I don't know. The problem here is, how do I even test this? Because I trained the LLM. First of all, how long should I train it for? And how do I know? I mean, it's probably going to be very similar depending on these. Maybe just the speed of training will increase. Maybe I can just measure that. How do I measure performance though? I guess I cannot just look at the loss function. I need to maybe use some benchmarks or something. I'm not sure. Like hella swag, that's good for small models, and it shows very like the quickest one that shows results with minimal training. So how do we measure some metrics? Which metrics do we measure to measure performance of LLM? First one is perplexity, so e to the cross entropy loss. But here I feel like we will not be able to distinguish. So this measures how well the model predicts the next token, but I'm not sure we can distinguish if it's because it's good model or it's because it's overfitting. This is the implementation. You can maybe skim through it, but it's not so important. Exact match accuracy. If you are doing classification or QA, so for example, hella swag, use for specific tasks. So you have like one sentence and then four choice question, or continue the sentence out of these four choices. And so LLM needs to choose which one. And then we have these benchmarks here: Blue Rogue, Meteor. So for text generation tasks like summarization, translation, I think these should be also good. For now, I think Perplexity and exact match, this accuracy, are what we even have coded. Then qualitative evaluation, human-like behavior. Maybe we can just sample baseline flow 32 and quantized int 8 and look for semantic consistency, grammar, coherence, length of response. Automate this with side-by-side generation from the same prompts. So I guess human would evaluate this. I guess then I could also check like speed and memory, but my main problem here is how do I measure the quality of the model? But speed and memory of training and stuff also. And I think I'm going to be focusing on creating the optimal fast training environment and system so we can train this fast, because I would imagine each of these versions would take a lot of time to train. So that would be it. I'm thinking for the next few things I need to do in my LLM is Apple's cut cross entropy. This will reduce memory, and then we will be able to just add more parameters, make the training better. And then maybe I can implement DeepSeek's hardware forward-backward pass at the same time in their DeepSeek v3 paper. That's optimization. And then maybe custom kernels for hardware or max performance. I call it obliteration. So designing custom kernels for every calculation, for multiple calculations, for this specific hardware that I will be using, and for the specific LLM architecture. So this makes it less generalizable, but that doesn't matter. We want to squeeze out every bit of performance. So which other optimizations? And is it possible for us to eventually reach a Llama 3, like 8B or 1B or 3B level of performance? Because usually in the last 5 years, the optimizations made training of the model million times cheaper. So $10 million 5 years ago can be now trained same model for $10. So maybe we are a few years in, and maybe if the progress is even faster, maybe this time around we can maybe train Llama 3, 1B or 3B or 8B performance, these models. So that's how I see the future of our own custom LLM. It's gonna be made for anybody to train it for just a few dollars or for free from scratch, and then easily do research. I don't know, maybe eventually even for commercial purposes, I don't know, or for easily training your own model for commercial purposes. So follow me on YouTube to follow my journey, my daily vlogs about building this LLM from scratch, and you can learn how to do it yourself as well. And on Bilibili, Vuk AI, that's my username here. Thank you for watching, and see you in the next video.